He will present today spline-based freeform shape optimization workflow. Mr. Schöps, Dr. Schöps received his master and PhD degrees in mathematics from the University of Wuppertal in Germany in 2008 and 2011. He then joined the Technical University of Darmstadt as an associate professor in the Department of Electrical Engineering and Information Technology and Computational Engineering Group. His research interests focus on coupled multiphysical simulation, bridging computer-aided design, and simulation parallel algorithms for high-performance computing, visual twins, and uncertainty quantification. So I'm very honored to present and welcome Dr. Schöps today. Mr. Schöps, I will let you share your screen.
Thanks for the nice introduction. Thanks for having me at the conference. And I'm also honored to talk about some of our research. You mentioned already the title. It's a spline-based freeform shape optimization workflow. I've split the title into 3 lines on my first slide. So it will be indeed about splines. So that's about geometry. It's also one of the themes just mentioned. I mean, it's bridging finite element world and the CAD CAD-based world. Then I will talk a bit about optimization. I will try to not torture you too much with the mathematical details of our shape optimization algorithm, but I will talk a bit about it. And then that's most probably the most interesting piece for you guys here. I will talk about the workflow, and in particular, I mean, if I say workflow, I mean workflow and integration with JMAG. It's a joint work together with Melina from my group in Darmstadt and my colleagues Peter Gangel and Christiane Mellack from Graz University. So the talk is quite usually structured. I will give some motivation in the beginning, then I will talk about geometry, shape optimization. I will show you 2 examples, which are maybe a bit simple for your taste, but they show what can be done. I mean, it's basic research that we do, so it's not a product that we are selling. It's indeed university fundamental research, but I think it shows nicely what can be done, and then I will conclude the talk. The motivation actually starts where we left the conference on Tuesday. It's about additive manufacturing. It was presented by Dr. Jung, and I think he's, of course, completely right that we have new possibilities and new design freedom when we use printing for machines. We can create designs nobody has done before. And there's many scientific research in that field. I mean, I picked one more or less random but nice publication on the topic I show here. And I show one picture basically from additive drives where they showed a nice printed coil. So these are motivations that we have new design freedom that we need to exploit, and we need to have tools, software tools that exploits basically this. What we nowadays typically do is that we do parameter optimization. So we change a width, we change a height, we change the radius of a machine. And I think also there was a session in the conference about templates, right? I mean, many machines are designed starting from templates, which is good and which makes totally sense, but it definitely does not unlock all the possibilities that we have, because the template can only do what the user or the designer has foreseen. So the next thing would be shape optimization. That's what I'm going to talk about in this talk. So you change the shape in some arbitrary manner. So you can have additional bendings, you can have additional curves whatsoever. And eventually, I mean, another even bigger step would be topology optimization. But current topology optimization suffers a bit from a background mesh that you typically need. So these pictures, by the way, are taken from a paper seen below. I mean, I modified them, but they're essentially taken from this also interesting paper. So what I'm going to talk is about shape optimization. So my design that I want to derive is based from a design that you guys might have come up with, and you want to slightly change the design to be even better. But you do not introduce additional holes, for example. That would need topology optimization. So the algorithms I show you now do not create additional holes or different material designs or whatever. To get started, I like to talk a bit about geometry. I said that in the beginning. And what you see here on the left is a spline curve. I mean, I guess all you guys know what splines are, but I put the word spline to my title, so I think you deserve a bit of explanation if you do not know what a spline is. A spline is a piecewise polynomial, but a polynomial that is nicely glued together. And all the CAD tools that you use, so also JMAG and many other tools, are based essentially on spline-based technology. And splines are quite convenient. I mean, they come from automotive industry originally. So I think Citroën was one of the first companies to use splines for the outside design of their cars. And you immediately see that splines are very useful because you can locally change the shape of a curve. I mean, I do that right now here, right? And it follows smoothly, and it follows locally. So we can locally change the design of a curve on a computer, and you can change also how smooth you want to have the curve. So if I go here to lowest order, meaning 1, you see we have edges, we have rough corners, but we can have also this in a design, but you can also increase the smoothness and you get a very nice and smooth design. So originally this was invented for humans to modify, as I said, the outside, the shape of a car, for example. And for a machine, I mean, the design in terms of optical beauty might not be as relevant as for the outside of a car, but nonetheless, now the computer can change exactly what I've shown you before in an automatic fashion. And that's why I think they are very interesting. Splines are very expressive. So for example, you can represent circles exactly, which is very, very relevant also for electrical machines, for example. I said I do not want to bother you too much with the mathematical details. So I talked about splines. I talked about B-splines to be precise, and even more precisely saying it's NURBS, non-uniform rational B-splines, which are, and that's what this formula says here, are essentially splines divided by splines. This is necessary because only those guys can represent a circle, for example, exactly. But anyway, keep in your mind a picture like this. So you have piecewise polynomials, you combine them, and they give you a beautiful shape, and eventually even a circle. I think I said most of this, but maybe you can generalize this concept from 1D curves to surfaces and also to volumes. And that's actually what we're gonna need for our machine. So our machine will be represented by splines, giving us, I mean, in 2D, it's surfaces, or if it would be a 3D design, it would be even a volumetric representation. The beauty is now, if you move the geometry also, I mean, if you move the splines and you have a global mapping of the machine, you do not have to do remeshing. So if you change the shape of your machine, the mesh will just follow automatically the different modifications of the shape. And that's quite cool, right? Because you all might have observed, if you remesh a model, you might have slightly noise, you get small noise, right? Because of the mesh. And all this goes away if you smoothly modify the mesh according to the geometry. There are also some other nice features if you use splines. So obviously, I mean, it's super exaggerated what I show on the left, but this is essentially what happens if you discretize electric machine with a very coarse linear mesh. Of course, you do not capture the curvature exactly, but that's no issue if you use splines. So on the right, you see they map the whole domain to a curvature. So just to be very clear, I mean, I think no commercial tool, I mean, all commercial tools use in the cut engine to use the splines, but there's pretty much no commercial available tool that uses this for the analysis and the shape optimization yet. So that's what I mentioned. I mean, it's, I think, a very interesting technology, but it's definitely not, I mean, it's fundamental research that we're doing here, and it's not yet commercially available, to my best knowledge, actually. It gets even more difficult if you want to do 3D designs, because most CAD tools use surface representation. They call that boundary representation, BREP, that's the word. And they don't do 3D volumetric, or sometimes called trivariate spline geometries. And that's the thing that we are working on. I will not talk about this in this talk, because this is something we cannot yet bridge with existing tools. I mean, in the 2D case, we can make a nice workflow with JMAG, but for 3D, we could not do it. So that's ongoing research. But I think that's the key. That's the key for 3D printing, because essentially, what people that do 3D printing will need is a volumetric description, right? You have to print also in the inside. It's not sufficient to print the outside of a shape, right? And that's why you need these kind of trivariate representations. And there are also nice papers on this. So for example, here, rather recent one from 2019 from Dokken about the trivariate spline representations and additive manufacturing. So I think that's a key simulation technology to even allow for more crazy shapes to be printed in the future. Right, so I told you about the splines. I told you how to move things. That I think that is a very nice tool. You can easily control the smoothness of your curves, so you don't get a strange checkerboard pattern that you get with maybe other algorithms. So I think that's all quite convenient. And that's the workflow that I am going to show you in the following. So you can create a CAD geometry. You draw something. You can do that in JMAG or any other tool that allows to create geometries. I will not name any other company, so we stick with JMAG here. And then you can export the geometry using some IGES format, DXF. I mean, you choose an export format that you have. That can be read currently in our software. You get a spline surface representation. then we can use our software to compute derivatives and to optimize the shape, and you get something different after the optimization, and that can be then passed again into JMAG by import. So that's like how the workflow is working right now, and then you can do all the nice post-processing in JMAG as you're used to. Now, 2 slides, a bit more detail what we are doing. I mean, keep in mind that I allow in my optimization to move every point of my geometry. Every point can move somewhere. That means you have infinitely many optimization parameters. Even if you restrict that to all the control points of the spline, there are hundreds, easily hundreds of degrees of freedom in the optimization. And it's quite natural, I think, that naive algorithms that work nicely with a few parameters, like swarm algorithms, will not perform very well with these kind of huge spaces of parameters. So what we do, we use a shape sensitivity based algorithm. So you really compute a derivative. And this is the definition. So you modify your domain, the geometry of your machine, you modify that, and then you define it's the basic concept of derivative. You have a modification, you slightly perturb your geometry, then you evaluate the quantity you want to optimize, and then you divide by a smallness parameter. So that's essentially the definition. And then you obtain a directional derivative, if you like. It's called W. And this W gives you the direction in which you have to change your geometry to improve your goal functional J. And on the right lower corner, you see an example of a piece of a permanent magnet synchronous machine's rotor. And you see in dark red the regions where we determined a large derivative. So there's a lot of movement is necessary. And you see some arrows. I hope at least that you can see the arrows. And they point outwards here in the center, and they point inwards there and there. And that means, okay, we have to modify our design according to those arrows to improve the shape for this specific J, let's say. And this can be indeed numerically computed. I mean, what you have to do, you define a bilinear form, which is essentially the same kind of problem that your fine element code JMAG is solving anyways. Since a bilinear form is positive, or this one should be positive definite, then you know that's positive. So that means if I shift the minus sign to the other side, you can see here that I get something positive with the minus sign. This shall be, or will be smaller than 0. So that means we have a descent direction. So moving the control points of our motor geometry, a small piece into some direction will decrease our goal function. Okay. That's the idea, and that gives us the derivatives, and that gives us a new design, even though we theoretically move every single point in our domain. I promised I will keep the mathematics short. I'd like to show you some examples how this can work in practice. So first problem, we want to minimize the total harmonic distortion of an electrical machine. So we have a minimization. We have a goal functional. The goal functional is the THD, total harmonic distortion, for some selected index of frequencies that we consider. And we have the electromagnetic force as a quantity. It's time dependent, and obviously it depends on the shape of our geometry, of our motor. And then we might have additional constraints. I mean, the EMF is the quantity we are looking at, but there might be also geometric constraints. There might be a constraint that we want to maintain the same torque or whatever. And then you get additional subject to additional constraints. So indeed, I said we do, I mean, that's just standard stuff, right? We do a Fourier transform of the EMF, and then we do a total harmonic distortion. So we compute this square root of summed up coefficients of our Fourier transform. And that we want to minimize. And indeed, we did that for this, I said, rather simple geometry, but nonetheless, you see the original design that we started with on the left, and you see that in this particular optimization, it was a no-load situation. And by the way, this model was only linear, which is not a big restriction in the method itself. It's rather a restriction of our current implementation. We didn't do the nonlinear loop, but that can be easily fixed, but it has not been done yet. So it's a linear optimization, so no BH curve was considered. Anyways, so you see that the shape has slightly modified, and you see the small bump here, and you see small indentations on the left and on the right. And that's exactly where our derivative was pointing us at. And if you magnify the effect, you see that you get a very strange shape, and maybe humans would not have thought about it. Although I recall on some recent conference, people also proposed similar shapes, let's say, with sinusoidal modifications by classical, let's say, not artificial intelligence, by classical intelligence, let's say. But this comes just out naturally from the algorithm. And this can be, as I said, then imported back into JMAG. So on the left, you see the original design, and on the right, you see the modified one with a small bump, for example, here in the center. Right, and that's the results that we got. So we did this optimization algorithm. We started with a THD of 0.1, and we could significantly reduce it, so somewhat to 0.02. You see the green curve is our in-house code that we used with this spline-based technology. You see the orange dot here for the original design. That's JMAG computation using linear setting. If you do a non-linear setting, you get the green dot. And you see for the optimized geometry, after 50 iterations of our optimization algorithm, you see that still the linear JMAG computation and our code still correspond rather well, I'd say. But you see that the nonlinear computation got even slightly worse, I would say. The difference is a bit larger here than there, but that's expected because we optimized the geometry for a linear setting. So our optimizer did not know about BH curves and so on. So this is just a shortcoming of the implementation, as I said before. And you see that we significantly reduced the THD. I mean, here we see the Fourier spectrum, and you see in red and orange the in-house code result and the one from JMAG. And you see in green and blue the optimized geometry results, again, for our in-house code and for the JMAG one. And you see they pretty much agree quite well. And you see that we especially reduced the 9th and 11th harmonic significantly by this optimization. If you go to the nonlinear case, you see that we still significantly reduce the 11th harmonic, but not so much the 9th. And that's why we gain less in the nonlinear setting. But as I said, that's what needs to be expected, I guess. And that's actually what you do not want to have for the presentation. So my Acrobat reader decided to not show you the machine. But let's see if I can fire it up again and show it to you. I'm sorry for that. Okay, Acrobat seems to be angry with me. Yep, here we are, back again. Let's see if the second try works better. Yep, you know this. And here are the machines. And they are not turning. Well, they are turning, but very, very not smooth. But that's not because the computation was bad. And it happens again. All right, I will not show you this slide again. I'm sorry. These are nice results I obtained by JMAG. It's a bit of a shame that I am not able to show you these animations, but I think you get the picture. So I will show you a second example of an optimization. And luckily, there are no movies. There are no more movies. So I think I'm safe now. Right, so second problem, we maximize the torque. That's a joint work with the colleagues in Graz. And they wanted to optimize a synchronous reluctance machine that was a dedicated design for an X-ray tube. And here you see the initial geometry that Christiane designed. And you see the torque, and now the design, the idea was to optimize, and on the right lower corner, you see the directions of the derivatives again, and you see it wants to move here pieces of the rotor. And indeed, the algorithm did this. So on the top right, you see the result of our in-house code after the optimization, and you see the differences in the shape. That was quite fast. It took 10 minutes, and the best design had a torque of 1.26 Newton meters. And then afterwards, what we did was we parameterized in JMAG the geometry in a similar fashion, such that the design would allow to create a similar shape. Right in the beginning, we didn't foresee, we didn't foresee these kind of parameters in the design. So there would have been no way for JMAG to optimize towards this goal. But once we knew that this is an interesting shape, you can modify the template, you can introduce additional parameters, and it ended up in 36 geometric parameters. And afterwards, I mean, there's a small difference in the best design, but in the torque, but that's like negligible. That might be also due to the different results of the different codes. So it took way longer in JMAG, but that's not, I mean, that's possibly, first of all, our fault because we didn't set up the optimizer with the optimal parameters. And secondly, of course, there are quite many parameters, so it's not surprising that this takes quite long. So, but this is not about the computational time. It's about that you have a design you might have not foreseen. So I'm sure some of you guys in the audience might have said, well, that was obvious to get this design. Maybe yes, maybe for you, yes. But just imagine for different scenarios, it might be less clear. And this algorithm will still give you a nice answer. And this was recently presented by Peter Gange and Christiane Mellack at the ICTE symposium. And I think they're writing a proceedings about this. So also on that topic, you will see, if you like, a publication rather soon. Right. So conclusions. I showed you a spline-based simulation and shape optimization approach of machines. People have done this before, but I think nobody until now used the spline technology so consequently as we did. It allows you to freeform shape optimization of the rotor. It might give you designs you might expect, but in other scenarios, it might give you new designs you might have not expected. We showed for two rather simple examples that you can reduce the THD significantly. And on the other hand, we increased the torque also quite significantly, I would say. The beauty is about the splines is it's very easy to include this into commercial software like JMAG. So it's very natural. And we built up a small workflow that can do this. And he validated all the results also with optimizations within JMAG. What is missing, what we'll do next, what we are working on is indeed to do this for 3D, that we do this in a robust way, right? Including tolerances. I recall there was a question to Dr. Jung on Tuesday, what are the manufacturing tolerances for printing, right? So, I mean, there might be some, and if they are, it would be nice to include this in the optimization immediately. And yeah, maybe the easiest part on our side is to add nonlinear material relations, but that's just that's a tiny piece, but that needs to be done on our side anyways. Please, I mean, I can show you also the references, but let's maybe keep that one here, and I'm happy to receive questions. Thank you.
Thank you very much, Dr. Schöps. This was very descriptive, very graphical. This is a nice presentation. Thank you very much.
Thank you.
Now we will switch to the question part. I'm sure we will receive questions right now. So far, we didn't have anyone.
I hope nobody asked to see the movies again.
Okay, we have the first question.
Yes.
Is there any advantage difference compared to topology optimization?
It depends. So typically, the topology optimization doesn't give you immediately a spline representation. I mean, it really depends how you do the topology optimization. But the simplest approach are these on and off approaches. And that gives you a shape, but it's basically, in the simplest case, it's just bricks, right? That you switch on and off. So in the end, what you get is just these bricks. So even if you have done a topology optimization, you might want to do a shape optimization afterwards to get a nice smooth curve for the geometry, right? You want to have a cut geometry in the end. So I think it's not about advantages. It's like complementary. I mean, they work together. And also in this approach, one could also introduce different topologies. So I would not say that's an advantage. I think they have to go with each other, at least if you want to unlock like the most crazy designs. Because as I said, in this approach, we are still stuck with the topology that the designer has given. And I really think that the next step is to also change that. I hope this answers the question.
Okay, thank you very much. Now the next question. How difficult is it to include manufacturing constraints in your algorithm? Minimal thickness and minimal radius?
Not difficult. I mean, you can really define any function as a constraint. I mean, this can be done. I mean, we didn't do it, but definitely once we want to go towards additive manufacturing, we have to do it. But no, there's no, I mean, essentially, we use this gradient-based algorithm, but essentially, I mean, what you could also do if you prefer, you can just use also any other optimization algorithm and move the control points of the splines. And essentially, you are back in a more traditional setting. And also there, you could define distances between these control points as constraints. So it can be done, but we didn't. I mean, it's from a fundamental research perspective, these are all very important things, but it's just, you know, I mean, if I put 2 constraints more, the next person asking for another one, and in the end, it becomes very technical, but it's theoretically, there's no restriction of that.
Okay, thank you very much.
Just a matter of doing.
And we have no more questions. I think we'll wait another 1 to 2 minutes so that everyone has a chance to ask their questions.
Yep.
Okay, we have another one. In JMAG, the on-off method is available, but also the density method. Is this similar to your method?
So if we would include topology optimization in our approach, it would be rather like the density one, indeed. So also specifically our co-author, Peter Gangel, he worked a lot also on that. So indeed, this can be combined with the density approach. So it's not really the same, as I said, because this approach is in some sense, maybe even inferior because we cannot include the holes, as I said. But that was not the point. My point is I want to create a geometry that I can give immediately to the guys of additive drives and that they can immediately print the design. So it's a bit of a different focus. But I think we actually started to include this with the density method. So the on-off approach is really, to my feeling, is like the opposite of the spline approach. It's like, you cut your machine in small pieces and you switch it on and off. It's like the opposite. So the density approach, in conclusion, is a bit like what we do, but we have not yet considered this. So we are just moving shapes, as I said before. It's not the density method, not exactly, but it's related in some sense.
Okay, thank you. Next question, are your algorithms open source?
Yes, indeed. I mean, we have not yet published everything, but it's based on open source software. And the one paper I mentioned maybe at some point on one slide that we have published, once this paper is through the review process, we will make this stuff available on GitHub or whatever. So yes, it's fundamental research. It's funded by public money, so it will be open source, yes.
Okay. How would the algorithm react to material deterioration due to manufacturing, which can be computed in JMAG, boundary method for stamping?
Okay, I have to improvise. I'm not sure if I get the question. So it was about manufacturing tolerances again, right? So, I mean, material deterioration. So what I thought of most of the time is manufacturing tolerances in terms of shapes, right? I mean, because it's more a shape thing. But on the other hand, I mean, there's no problem in having the material to include also uncertainties in the material in the optimization algorithm. So it's just possible. I mean, it might even be easier because the tricky part is typically the shape. I mean, for the materials, it's the uncertainty, the modeling of the uncertainty that's difficult, right? I mean, you have to have the right deterioration curves and so on. I mean, that's super difficult. But once you have those, I think including this in the optimization, I'm not scared. So that seems to be rather doable. And that's independent of this approach. I mean, I think that's generally not so difficult, I would say. Getting the curve, that's the hard part. Getting the data to fit the deterioration curves, that's a hell of a work. But luckily for me, that's what the practical guys have to do, right? I mean, from a computational perspective, that's not the challenge, I think.
Right, you have answered this question. Next one, can we predict the machine performance?
Yeah, I mean, what means performance now? I mean, yeah, I would say yes. I mean, we compute the torque, we compute the THD. I mean, whatever other quantity you want to compute, you can include that in the optimization. And theoretically, I mean, I showed you single objective optimizations. You can also go further. You can have bi-objective optimization or even Pareto front optimization. And then, I mean, your performance. I mean, what means performance, right? I mean, it's a combination of key performance indicators, right? Of key KPIs, and you can build combinations of that. So yes, definitely. I mean, that's all about, I mean, that's what JMAG does, right? It predicts the performance of the machine, yes. Or maybe I misunderstood the question, I don't know, but I would say yes.
Okay, we have another comment from, it just says in the sense of FEA, but no more questions towards that. Maybe he's still typing.
Okay. I mean, so this spline technology is essentially, I mean, some people call it IGA, isogeometric analysis. It's a term coined by Tom Hughes in the US. I mean, he's more or less the inventor of that idea, I would say. And he's also one of in the mechanical community. So I'm not sure if he's well known in this community here, but the mechanical community is one of the FEA well-known experts. And yeah, it's FEA, but we use splines, but it's essentially finite element analysis. So there's no big discussion about that.
Okay, then do you think such methods should be embedded in commercial software?
I hope. I mean, that's what we do for research, and I hope that in a few years, I mean, if the technology becomes more mature, I mean, it's also about this technology readiness level, right? And we are not yet ready in the sense that you can immediately use that as a black box in the commercial software. But I think it should be, and I think it will be. I mean, I think that more and more companies will. I mean, the CAD kernels especially. I mean, they have to start, right, to have 3D representations of the geometry internally. And I think that will happen. I mean, as I said, in the mechanics community, they started a bit earlier with these topics because for them, obviously, they have different challenges, right? Because of deformations that you have to simulate car crashes and so on. And I think in that community, they have started, but it's also there at the beginning. But I think they will first have this kind of technology in commercial tools available. I mean, let's say crash tests or whatever. And I think that tools will do this, yes. Or I hope, and I think it will be a good step. Let's see. Maybe you should ask us that question to the JMAG people, actually.
Okay, thank you. Next question. What about numeric noise of the FEM code? Any differences to other algorithms?
Yeah, I think I tried to make that point that if you use these splines, some part of the noise comes from the mesh, right? I mean, mesh noise. If you remesh a design, you make a slight change of the geometry, and you run the mesher again, and it depends how the mesher is implemented. If it's very small changes, the mesher might move the control. I mean, the mesh points might move it according to the geometry. Then it's a bit more clever. But if it's naive, then it will remesh the whole geometry, and it might come up with a rather different mesh. So in some sense, it's deterministic, but in the sense that for the same geometry, you will get the same mesh. But it's not really predictable how the mesh changes if you change some piece of the geometry by a tiny piece, because meshes are also to write a mesher is very complicated. Meshing is not an easy issue, and all of you know that meshing is a nightmare sometimes. So of course not with JMAG, but generally meshing is difficult. So this kind of noise is indeed removed by using the splines, because if you move the splines, basically all the mesh follows naturally. So I think that's one advantage, yeah, definitely. And it reduces this kind of noise indeed that is available in finite elements if you move geometry pieces around. Other noise is the same. I mean, essentially it's a finite element analysis just with slightly different technology, but it's finite elements. So you have all the same issues. If your mesh is too coarse, if you don't resolve the skin depth somewhere, I mean, you are in trouble. And that's the same here. I mean, there's no free lunch, let's say.
So additional to this question, Mr. Niels Doman added, but you may warp the mesh too much.
True, of course. I mean, yeah, I agree. If you do really, really crazy deformations, also the splines cannot cure you, right? I mean, if you really move, I don't know, even if you make intersections and so on, then you're in trouble. No, indeed, no. I mean, that's good that you point that out. So of course, there's no magic. So if you have large transformations, you might have to remesh your domain. Also with spline technology, yes, of course. But I mean, you have seen what changes we made, what we had, and these were like tiny enough to have not affected the elements. And what we do, I mean, we deform the overall mesh. So if you do it very naively, you would maybe just deform the outer layer of the elements, let's say, if you change geometries. And that's, of course, even worse, because then you have all the change in geometry is just spread out over one layer of elements. That's not going to work. So the splines automatically spread this out over the whole domain. So that's already some relief, but of course, at some point, yeah, I mean, if you move things crazily, you cannot anymore capture this with the same mesh. That's true. I agree.
Mr. Niels Doman said, thank you.
Okay, welcome.
Okay, looks like we are out of questions. So last chance. If you have any questions, please ask them now or write Mr. Dr. Schöps our email.
You can use this platform thingy or use conventional old email or a postal mail if you like. All possible.
All right, I think this it. I will check again. So no one gets an unanswered question. Okay. Yes, I think this is it.
Yeah,
Again, thank you very much, Mr. Schöps. It was an honor to have you here. Very interesting topic. And to our viewers, thank you very much for the interesting questions and the lively discussion. And yes, hope to see you next user conference again. And please join in to the next session at 11. We have PSIM implementation for modeling the solar-based grid-fed converter. And we also have great, interesting presentations in the afternoon. Thank you very much. Thank you very much. Bye.